So this beginning part might be boring for some of you guys who have done some brain interfacing in the past, but I want to do like a quick dry run through at least the simple technology and science behind interfacing the brain, and then also talk about like where the industry is, who the big players are, the difference between medical grade EEG and then commercial and DIY stuff. But before I get started, I want to get like a better understanding of the demographic of who's here. So how many people have experience doing any work with brain-computer interfacing prior to this? Go ahead. Cool. All right, good. So how about experience coding in any language? Nice. Good. Very good. Okay. Arduino? Who brought Arduinos? Okay. So we'll probably have about that many groups. I have a few to go around. So who here knows of like the Frontier Nerds hack? Nobody? The Frontier Nerds, they did how to hack toy EEGs. Okay, good. So this is going to be like fun and fresh for everyone. Anybody work with emotive? Any emotive people? Okay. Did anybody bring an emotive? Let's see. So I'm assuming that the answer to this question, does anybody have a BCI project that they're bringing in that they want other people to work on? Or have ideas already? So okay, cool. So at the end of this talk, I want like ideas, you guys let ideas fester in your head while I'm talking. And at the very end, we're gonna do like a mingle session where you guys talk and then come back in and people are gonna do little pitches of project ideas to hopefully recruit people onto your team. And that'll be that. Come on in, sit down. I was just giving the competition teaser. So at the end of this, I'm going to let people present ideas for projects for the competition. Okay. So without further ado, let's get started. Boom. Okay, so this is Interfacing the Brain, presented by the Brain Interface Lab, recently founded, and Workshop, who's an MFA-DT group that helps us organize events and stuff like this. So what is a brain-computer interface? Question mark. So there's a lot of different types of brain-computer interfaces that range from very invasive to not very invasive. So ECOG, which stands for electrocorticography, is planting electrodes directly against the surface of the brain. And there's some really amazing things that people are doing with this, but there's obviously a lot of like risks and ethical considerations about making this commercial. But you know, they've had people that have been able to control robotic limbs or basically move things with precision that they wouldn't be able to use 10 years ago. So then there's fMRI, which is functional magnetic resonance imaging, which is basically just taking scans of the brain. But obviously, you can't really have someone walk around with an fMRI, so that's one big limitation. And then what we're going to be focusing on today is EEG. But even EEG has a big range of like, kind of like what's practical and what's available to the DIY. So like this guy right here, this funny looking dude, is wearing like 256 EEG electrode contraption. So each of those little things next to his head is a single electrode that's measuring voltage potentials or potentials against the scalp. So there's like the medical and research grade stuff, and then there's the commercial stuff, which is what we're going to be going around. So EEG breakdown, electroencephalography. Now, is the recording of electrical activity along the scalp. EEG measures voltage fluctuations resulting from ionic current flows within the neurons of the brain. So it's the least, at this point in time, it's the least invasive method of neurofeedback because you don't actually have to put anything in the brain. What you're doing is you're recording the electrical potentials of neurons firing inside the head and kind of like splashing against the skull. So commercial apparatus, NeuroSky, Emotive, and Interaxon are kind of like the three leading commercial companies right now that are putting out low-cost EEG equipment. And these are like actually the first ever recorded EEG signals by this guy Hans Berger in 1924. And at the time, there weren't even computers, and he was just like recording brain activity. And now it's much more prevalent because you can make it digital. So these these are various EEG power bands. And so what you'll notice is that they're categorized into these segments of frequencies. So 0 to 4 hertz is delta, theta is 4 to 8 hertz, 8 to 13 alpha. And what that means is it's really like as these electrons fire inside of your head, they start to add up, and they'll splash against your head or your skull at like various frequencies in these large clusters. And so the frequency of these clusters are categorized, or using FFT or Fourier transform, are broken down, so the wave is like separated. And then you get these very distinct patterns which become EEG. So there's a great EEG analogy that I found somewhere, and I'm going to read it to you. EEG bands are like little waves combining to create big waves in the ocean. As thousands of neurons fire, the little waves come together to create larger waves known as brainwaves. It is these dominant brainwaves that are measured by EEG devices. So I think that is a good visualization of what's going on inside of the head. Moving on. So applications of BCIS. Here we go. One second. So I'm going to click these links because they're really inspiring. It's like it just gets you kind of emotionally invested in a field. This right here is this paralyzed woman. Audio.
You're watching most of London's brain machine interface in action. Kathy Hutchinson is paralyzed and unable to speak, but just by thinking she's able to control the movements of its robotic arm and drink more than coffee. She's part of a pioneering study done by researchers at Brown University in the US.
People who are paralyzed, like a brain disconnect.
So, yeah, you get the idea. So she has an econ, basically an electrode grid implanted underneath her skull. It's not actually, they don't actually have to make an incision into the brain, they just remove a piece of the skull and they put the econ, basically an 8x8 electrode grid, against the surface of her brain near the motor activity region. And with that, they're able to train her to think certain actions and then compare that to her average brain state. And then she's able to train herself to move an artificial limb. Pretty amazing. Let's go back. This one's pretty cool. This is actually done with emotive, and these people.
Autonomous Labs proudly presents.
They built this kind of prototype of a brain-controlled car, and so what they were able to do was train someone to stop, go, turn left, turn right. So 4 basic actions with an emotive, which we have one today if people want to tinker around with it. I haven't yet, but yeah, also pretty awesome. So lastly, I want to show you this talk right here does a good job of explaining how these systems work in terms of recording average brain state and then recording a certain action or activity and then juxtaposing the two to find triggers for ERPs or which is an event-related potential. It's the acronym for that. Let's see if I can. Yeah.
Or even as complex as programming robotics. We have
Alright, so I'm skipping to a part.
the cognitive suite is to start with training a neutral signal. So with neutral, there's nothing in particular that Evan needs to do. He just hangs out, is relaxed. And the idea is to establish a baseline or normal state for his brain because every brain is different. It takes 8 seconds to do this. And now that that's done, we can choose a movement-based action. So Evan, choose something that you can visualize clearly in your mind. Okay, so let's choose pull. So the idea here now is that Evan needs to imagine the object coming forward into the screen, and there's a progress bar that will scroll across the screen while he's doing that. The first time, nothing will happen because the system has no idea how he thinks about pull, but maintain that thought for the entire duration of the 8 seconds. So 1, 2, 3. Okay. So once we accept this, the cube is live. So let's see if Evan can actually try and imagine pulling. Oh, good job! That's really amazing.
So she wanted to have him train to do something a little bit more abstract, so she has him imagine the cube fading out, which is a little bit harder to visualize. At least that's the way she explains it. And then it takes him about 30 seconds to get it, and he ends up getting it, and everyone's like, ah! So let's go. So these like are other awesome headlines of things that are happening with BCIs in the news. This is like drug-free ADHD treatment for children. So it's basically like tracking attention levels and then being able to find triggers for increases or decreases in attention levels in children, and then using that as basically like ADHD therapy. And actually, you brought up the Gen Space. I actually sent an application to them to undergo a project for this exact thing, and I got declined. But but I was like, I had the idea before these people. And then these are other. You already saw one of these, the truly controlled prosthetic arm. So this guy won this AT&T grant for using he actually hacked this really funny commercial. Like, I don't know if you've seen it, the Nico Mimi. Has anyone seen it? It's like these cat ears that respond to brainwaves. When he hacked into one of these and built an application that blocks phone calls when he's concentrating. So it's pretty cool. So yeah, okay. This right here is if you want to like stay up to date on kind of the most current and interesting projects, especially mainstream ones that are related to BCI. Neurogadget.com is a blog that's entirely dedicated to just like keeping the world up to date on BCI. So I would jot that down if you want to stay up to date. So now I want to jump into this kind of like commercial DIY BCI realm, which is what I think most of us are a part of, aside from maybe a few Colombian neuroscience people here. So it all started back in like, I think it was 2001 or 2002 with this project called the Open EEG Project. And this is still existing. It's got a lot of really cool documentation on open source hardware, open source software tutorials about how to build your own EEG, like ranging from every type of electrode, which is like active electrodes, passive electrodes, and we'll go into more detail in a little bit. So this is these were kind of like, these guys were the pioneers of bringing EEG out of the laboratory setting and providing it to like hackers, programmers, etc. Now this guy here, Eric Micah and the Frontier Nerds, this is the hack that we're going to be basing the hackathon on mostly, since most of you guys don't have any background. And I'm going to be going through this tutorial after this kind of intro presentation. But they took, actually I can pass this around right now, but you can take them out of the packages. But these are like the things that we're going to be using for the event, which are, they're basically like, Mattel made this game like the Star Wars Force Trainer, or the Dual Mind Flex, and it was this competition game where it was like you pitted two people against each other to like try and concentrate stronger to make a ball move in their directions. Anyway, they made way too many of them, and nobody ended up buying them, and now they're like overstocked everywhere. And so you can order these for like $40 for two of them, and it comes with a chip inside of it that if you order from NeuroSky itself, it costs $40 just for the chip. And you get like sensors, electrodes, an RF electronics, so it's like, it's definitely worth it to go this way.
What was that again? I'm sorry, what was that resource?
Sorry?
Yeah, what?
It's called a Mind Flex.
Mind Flex, okay.
So it's, yeah, you can look it up, it's called like Dual Mind Flex, or if you look at Star Wars Force Trainer, it's another toy also made by Mattel. But yeah, we'll go into more detail about that. So then, these are like the kind of the commercial big players. Emotive, and you'll notice they range from kind of like the most electrodes to the least electrodes. So Neurofocus is this new company that has this like, I think it's 26 electrodes, and they're really trying to get clearer data and more spatial resolution by having electrodes kind of all over the head. Then you've got Emotive, which is cheaper, less electrodes, so less resolution, and then Interaxon, NeuroSky, and X-Wave are Interaxon actually has 4 electrodes, and they ran a successful Indiegogo campaign for $150,000 that ended like a month ago. So they're I think like kind of the up and coming commercial vendor, and it's going to be really cool when they actually release the product in June. Which one was it? This is Interaxon, but the product itself is called Muse. It's called Interaxon Muse. You can look it up on Indiegogo. And then X-Wave, these guys haven't been as successful. I think it's because their models aren't as attractive as the other companies. So you'll notice that all of these BCI vendors have like pretty women that have like low-cut shirts that are advertising their brain interfaces. There's got to be some way to get into it. So these are like projects that have resulted from, these are actually all New York City-based projects that have resulted from kind of like the DIY brain interfacing craze. This one right here is actually really cool, and it hasn't happened yet, or maybe it's happened, maybe it's done already, but on February 25th, it's this project called The Ascent, and it's this big art installation where they hook one person up to this, like, all these cables, and then the person meditates, and their levitation level is, like, controlled by their brain state. So you should check it out, because it's happening in Queens, I think, on February 25th, which is a Monday. So that should be a pretty cool event. And I bet you it's going to have a lot of brain hacking nerds there. This one here, how many Hackman hack people do we have here? Cool. So, yeah, this was one that you guys did for the Maker Fair, right?
Yeah.
Yeah. So this was another successful, actually this one was a Kickstarter campaign, but this was really cool. It was basically brain pong to get two people. I mean, you guys can probably explain it later on better than I could, but I was really jacked up that this was successful when I saw it. And then these two projects here. This project actually is my project on the lower left, and it's the reason I'm putting it here is because it's like a derivative project of the hack that I'm going to show you guys. So I just took the Frontier Nerds hack, took the serial stream, sent it out via Bluetooth to an Android app, and allows the user of the Android app to like record the EEG data and then also timestamp it with other inputs like your mood and activities. And like I kind of like cut off, and I should keep going with it, but I'm not a great programmer, at least Android developer, so I ran into some hurdles. And this one here is by another MFADT student, Maxim, and this is a really cool. This is his thesis, and he built this this drawing tool called ELO, and it has it uses a NeuroSky MindFlex and then also, or a NeuroSky Mindset and then also Connect. And so you stand in front of the screen and you move your hand around, and the position of your drawing cursor is dictated by your hand, but then I guess the palette, like the color palette and the size of the brush are dictated by your brain state. So this is, I want to show some. So these are some of the pieces that were made by his tool. It's pretty abstract, but it's still a really awesome application of technology. And this project just got accepted into the future interfaces. Does anybody know about that? It's like the 15 MFADT people applied and only 2 of us got in, but it's like pretty, I guess, pretty prestigious New York City future interfaces, like demo days, and this project got accepted. I applied and didn't get it. What are you going to do? Anyways, so I want to make sure I finish on time. This is pretty well. Oh yeah. Okay, so what are the challenges? So the biggest challenge right now with taking BCIs out of the laboratory and the research medical realm is that increased functionality equals decreased wearability. And so you can see like this is medical grade EEG, but this guy's not going to be walking around on the street with this. And so this is like this graph that I came up with that I think represents the current state of the BCI world right now. So you've got this kind of like line of wearable brain interfaces to functional brain interfaces, and if any of these were either more wearable or more functional, they would be at the practicality point. But the problem is, no BCIs are practical right now. It's only people like us that are just like, let's do something cool with it, and you know, I don't know. That's about it. So the factors affecting functionality are like, biggest thing is signal to noise ratio and spatial resolution, and the factors that affect this are number of electrodes, obviously. So like, if you have a single electrode, you're pulling one stream of information from the entire brain, when really like various regions of the brain are doing different things at the same time. And so, you know, if you have 256 electrodes, you're able to compare, you know, every single region against every other region, and you're able to just, you know, obviously your matrices, your data set is much more complex. So then there's also the type of electrode. So there's wet electrodes and dry electrodes. Wet electrodes, obviously harder to wear because you have to apply a saline solution, but they conduct electricity much better, so your signal has a lot less noise. Active electrodes versus passive electrodes. Active electrodes, since you're dealing with like literally millions of volts when you're picking the signal up off the scalp, an active electrode has an amplifier at the electrode, and so it'll amplify the signal right away before the resistance of the wire is able to distort the signal. Whereas a passive electrode, a lot easier to wear because you need less hardware, has to send the signal through a wire to get to the actual processing device before you can synthesize the data. So these all like, it's kind of this like, where is the optimal point of wearable EEG? And then there's like placement of electrodes. You know, there's standard. There's this thing called the International 1020 system, which is basically the international standard for electrode placement. And like, you know, it was determined a long time ago. And is it still the most practical and applicable? And does it make the most sense nowadays? And I don't know for sure. I'm sure someone neuroscience can answer that question.
What's like, how do they decide where to put the electrodes? Based on chronology, or based on the underlying like brain areas?
I think, you know, like, that's a great question. I really don't know, but I think it's like, you know, like there's like the critical ones, and then as you get, you know, there's like, you know, if you have just a single electrode or two, you're gonna do like right and left, but as you start getting more electrodes, there's like tiers of critical electrodes, and then as you get to like 256, it's just like a sphere of electrodes around your head. But yeah, I don't really know the answer to that question. So factors affecting wearability. These are the examples of the attractive women modeling all the technology. So, yeah, you get it. So comfort, ease of use, like obviously, I talked to this guy, Eric Blue, who did a few brain hacks for quantified self. And I interviewed him like, why isn't, what's stopping brain and computer interfaces from taking off? And he's just like, they're uncomfortable as hell. So comfort, ease of use, cost, style. You know, like most people don't want to wear one of these things around and look like a cyborg. So this is again the BCI practicality curve, and this is like what I'm trying to push the open source community to strive to do, which is just take the cheap and affordable, available devices and like just make interesting enough applications to push this curve into the practical range. And I think it's possible. And I really think that the like us, kind of like the DIY open source community has as good of a chance, or like can affect this as much as medical, academic realms. So yeah, that's pretty much it. Like, you guys have questions before I jump into the tutorial?
Yeah, you got a bullet about availability of data up there before coming back.
Yeah.
So when you say availability of data, so under optimal conditions, let's say you do something in the research realm where you have, you know, wet electrodes that are all active, you have gajillions of them all over the head. What kind of data set are you getting from that? And from that data set, are you able to, or maybe the software isn't there yet, are you able to extract enough particular different pieces of information so you can, say, translate it into signals on the computer side and be able to do whatever you want from, you know, someone looking at, say, like a basketball versus a plate of sushi, and being able to have that kind of resolution to tell close kind of differences and then write code based on it.
Yeah, so once again, it all kind of like depends on the device that you're working with.
Well, I'm saying like in the best case scenario.
Best case scenario?
Yeah.
So some of the like the coolest things we've been able to do is you know, like implant electrodes into the brain and actually detect. So like one mechanism they use is to essentially like say things that trigger a response or trigger an emotional response, and they're able to detect that. So they were able to hack private like bank information out of people by saying like, okay, I'm going to get your 4-digit PIN code for your bank account. So the first digit of your bank account is like 0, 1, 2, 2, and they list all the numbers, and when the right digit comes up, people have an emotional, like they'll have a trigger, and they were able to get it with like 70 to 80% accuracy, or something like that, where they were able to pull people's PIN numbers out of their head.
Can I tell the difference between anger and happiness, or jealousy and disgust, based on brainwaves?
Like right now, I'm not really sure. I think, yeah.
So, it's really hard to quantify exactly like what we're talking about in terms of emotions unless you define it specifically with your study. And so it depends on the population, what you're going for, and like what you're using in terms of the study. So to say like jealousy is more about what brainwaves you're measuring.
Sure, right.
quantify
If you took a
jealousy.
baseline, if you took somebody and you found, let's say, an angry state, right? And then you took a measurement of the brainwaves, would you be able to say, okay, here's a baseline, we have enough resolution of data to say this is a baseline for anger,
Yes.
versus this particular configuration is a baseline for whatever.
Yeah, that's what they have on baselines.
And of course, the difference between individuals, because the structure is different.
That's why you typically look for outliers
Right.
to get your baseline values.
So that's possible today
Very much
with
so.
the high-end stuff.
Yeah.
With the high end, what we're talking about?
Well, with the medical
Yeah,
devices, but not with an emotive or a neural sky. You can't get
Actually,
that
it's
resolution.
becoming possible with that too. And that's what we're
And it's
talking
still like,
about.
there's a lot of things that can, like signal processing and kind of statistical analysis that can, over time, average out
Right.
kind of tendencies that end up tipping it to where it's statistically
So
significant.
better algorithms can allow you to get
Right.
more data.
And that's kind of like this, what's interesting, like the availability of data. One thing that I think the DIY community has the ability to like do better than medical or academic is actually making data available. You know, so you think about like Patchabet or, you know,